So now we're going at the more qualitative part of this chapter. We're actually looking at acid strength or acidity as a function of molecular structure. You will be doing this a lot in organic chemistry. You will be looking at Lewis structures of compounds and then from there predict which compound is more acidic over the other. But for 106, we're only going to look at three different kinds of acids: binary acids, oxoacids, and carboxylic acids. Now, before we begin, let us remember that the definition of a strong acid is something which dissociates completely as H plus, or which gives up H plus, which dissociates completely into H plus and some anion in solution. Okay, some anion called A minus. Now, there are, of course, weak acids which partially dissociate only into H plus and A minus, but the higher the Ka value, remember, then that means the higher the dissociation of H plus and A minus for weak acids. Therefore, our category for an acid being a strong acid, air quote strong acid, is whether a compound based on its structure can actually give up right away a proton. Okay, once again, our category for defining acid strength will be determining from the structure whether that compound can easily give up a proton. And again, there are various rules for the three acids that we're going to consider. For the first one, binary acids, they have this chemical formula HNA. Now keep in mind that binary acids here, the name for binary acids come from the fact that you have only two elements, H and A, H meaning hydrogen and A any other element. Okay, so if you have an acid with more than two elements, then that's not a binary acid, plain and simple. Okay, now the rule for binary acids is different from binary acids of the same group, the periodic table. Group, remember, is going up or down, or top to bottom, up to down, or bottom to top of the periodic table. And then same row, or row means you're going left to right or right to left of the periodic table. Okay, for binary acids of the same group, again, up to down or top to down, or down to up of the periodic table. So the rule is that the weaker, okay, the weaker the HA bond is, then the stronger the acid is. So let's actually write that down. So if, for again, acids, binary acids of the same group, the weaker, or let's say the lower the bond strength is between H and A, okay, the more acidic the binary acid is. And basically what this just means is, let's say for example you have HF, HCl, HBr, and HI. Okay, what that just means is the easier it is for you to remove H plus, the proton, from the bond, okay, then the more acidic a compound is, because you know it dissociates into H plus plus and anion. Okay, so that's why, for example, among these three strong acids, hydroiodic acid between hydrochloric and hydrobromic acid is air quote the stronger acid, just because the HI bond is weaker than the HBr bond, which is weaker than the HCl bond. And HF bond, the HF bond, so hydrofluoric acid is a very weak acid just because the HF bond is very strong. And the reason why the HF bond is strong, remember, is that fluorine is the most electronegative compound, okay? Or element, sorry, it's the most electronegative element. That's why for hydrogen fluoride or for hydrofluoric acid, the fluorine actually wants to hold on to those two electrons that are shared between itself and hydrogen. Okay, that's why hydrofluoric acid is actually a very weak acid. Okay, and then if you have binary acids of the same row, let's say for example methane, ammonia, water, and hydrogen fluoride, then the most polar of these compounds should be the most acidic compound. Okay, let's say for example, if you have a nonpolar molecule, methane. Okay, so there is an even distribution of these shared electrons between methane. I guess let's just draw the Lewis structure of that in 2D space. So remember that the Lewis structure for methane is this. Okay. Now methane being nonpolar just means that these two electrons are being evenly shared between carbon and hydrogen. These two electrons are being evenly shared between carbon and hydrogen as well. And now let's look at ammonia. The Lewis structure for ammonia is this. Okay. Remember that unlike carbon and hydrogen, which have similar electronegativities, nitrogen is more electronegative than hydrogen. So between this bond, there's actually a dipole moment pointed towards nitrogen. In other words, nitrogen actually here has a greater share of these two shared electrons. Okay, that's why there's a partially negative charge there, and a partially positive charge around hydrogen. Okay, and that is what this red region shows, meaning these shared electrons in the bonds are actually pulled towards nitrogen more. So when that happens, then this hydrogen, okay, actually has a weak hold of those shared electrons, and in return gets dissociated more. Okay, that's why ammonia is actually more acidic than methane, even though ammonia is actually basic. Okay, and then we continue the trend with water. Water is more acidic than nitrogen, just because an OH bond is more polar than an NH bond. And then finally, we have hydrofluoric acid. Hydrofluoric acid is actually the most acidic among these four because the hydrogen fluorine bond is very polar. Okay, just because fluorine again is the most electronegative element. Now, there's a rough rule for binary acids, and the rough rule is basically the higher the molar mass of the binary acid, the more acidic it is. But again, that rule stems basically from these two facts. That for binary acids of the same group, the weaker the HA bond is, then the more acidic a compound is. And then for binary acids of the same row, the more polar the HA bond is, then the more acidic a compound is.